If you've ever seen a perfect chart or maybe a flawless predictive model or even just a really clean dashboard, chances are you are only looking at the very tip of the data science iceberg. So today we are diving deep into, well, the other 90% that's lurking below the surface. We're talking about the hidden fundamental work that really determines if any algorithm succeeds or fails. And that's data management. Data science sits right at this powerful intersection of mathematics, statistics, and computer science. We tend to focus a lot on the math, right? The cool algorithms. But the universal truth, based on everything we've looked at, is that algorithmic brilliance means absolutely nothing if your input data is garbage. So our mission in this deep dive is pretty focused. We want to quickly get our heads around the core storage models, understand the frankly painful reality of data prep, and get a grip on the modern ways we handle these huge, messy data sets. And here's the statistic that honestly, it's kind of shocking. Every professional really needs to internalize this. The method for data projects is pretty standard now. There's the crisp DM framework that lots of people use. But the phase called data preparation, some people call it data munging, it typically eats up around 80% of the entire project timeline. 80%. I mean, that number alone tells you exactly why data management is, well, it's the bottleneck, isn't it?
It absolutely is the gatekeeper. Yeah.
Yeah.
And that 80% inefficiency, it often comes down to one simple distinction. See, a raw data point on its own is basically useless. It's just, string of characters, maybe 45. It only really becomes useful information when a system gives it context. So when we link that 45 to an object, maybe a time, a specific property, and importantly, a unit of measure. And that's the whole point of a database system, really, to provide that context, that structure, and control. It's about overcoming the problems you get from just, stuffing files into an archive somewhere.
Okay, right. So let's unpack the architecture then. For, gosh, half a century, data management basically meant one thing, the relational database. This model, introduced by Edgar Codd way back in '71, it brought some much-needed rigor. But tell us, why was that strict structure so appealing at first, even if it, became a limitation later on?
Well, it was appealing because it delivered integrity. That was the key. The relational model, it stores information in tables, which are technically called relations, and it demands really strict adherence to rules. The most famous one is the first normal form, or 1NF. And this sort of non-negotiable part of 1NF is that all the values in your tables have to be atomic. That just means indivisible.
Atomic, indivisible.
Yeah, think of it like this, right? 1NF is like storing your sugar and your flour in totally separate, clearly labeled containers in your kitchen pantry. It's incredibly neat, you get rid of redundancy, and it really helps ensure consistency. And this whole world runs on SQL-structured query language. You use it to do things like select data, filter it, and crucially, the join operation. That's how you link those neat, separate containers back together when you need the combined information.
Okay, so the system is perfectly tidy, but like you said, if you want to bake a cake, meaning do some actual analysis, you've got this complicated multi-step process of joining tables together. That sounds slow. What was the critical breaking point there? Where did it start to fall down?
Exactly. The rigor, the very thing that made it good, eventually became the constraint. That atomicity rule, it makes it incredibly difficult, sometimes impossible, to represent complex, modern kinds of data. Data that isn't perfectly neat and uniform. If you try to store things that have their own internal structure, maybe like a list of skills for an employee or a dictionary of nested user preferences, or even just large multimedia files, we call those BLOBs, the relational model either just breaks down or becomes painfully slow. And while normalization is great because it eliminates redundancy, which helps operational consistency.
Right, that's the good part.
Yes, but it also scatters related bits of information across potentially many, many tables. So for analytical work, where you often need to see the whole picture of something, like a customer, all at once, having to run these really intensive join operations across maybe dozens of tables, that's just a massive performance killer.
Okay, and here's where it starts to get really interesting for modern data science, right? The birth of NoSQL, which literally means not only SQL, and it popped up specifically to handle these complex data types and, importantly, the need for speed. It basically tells that strict 1NF rule to take a backseat.
Precisely. Yet NoSQL essentially throws out those strict requirements of atomicity and homogeneity. It trades that rigidity for flexibility and often speed. We usually group them into different families based on how they structure the data.
Yeah.
So you've got key value stores. These are generally very fast and simple. The value part that's attached to a key doesn't have to be simple. It can be complex, like a list or a vector, pretty much anything. Then you have document databases. These often use formats like JSON or XML as the main unit of storage, and these are fantastic for things like one-to-many relationships. You could store, say, an entire customer record and all their past orders within just one single document, which is obviously much, much faster than doing potentially lots of joins in a relational system.
Right, avoids all those joins. And what about the ones designed specifically for connections, for relationships between things?
Yeah, those are the graph databases. They're built from the ground up for data that's defined by its relationships. Think nodes, which are the entities, and edges, which represent the links between them. So if you're trying to query something complex, like a social network, maybe find the friends of friends of friends, a graph database can handle that kind of query exponentially better than a traditional relational system could ever hope to. And then finally, you also see triple-oriented systems. These are pretty prominent in the semantic web area. They use these subject-predicate-object triples, often in RDF format, and you query them using a language called SPI-RQL. That's all about capturing structured meaning and linking data together.
Okay, let's pivot back to that 80% problem we mentioned, the data preparation. If we're spending that much of our time cleaning data, we really need a clear standard for what good data actually looks like. How do data scientists usually benchmark quality?
Yeah, there's a pretty widely accepted standard, often summarized by the acronym ACUCVT. It stands for the 6 key qualities you're looking for. Accuracy is the value correct. Completeness are their missing bits. Uniqueness are their duplicate records floating around. Then consistency, does the data make logical sense within itself? Validity, is it in the right format, like a date looking like a date? And timeliness, is it recent enough to actually be useful?
Okay, ACUCVT. Let's focus on maybe the 2 biggest headaches in that cleaning process. First one, missing values. NULLs. These seem like silent killers because they can seriously skew your statistics, your averages, everything. What are the common ways people handle them these days?
Right, NELLs are a huge issue. Well, deletion's the simplest approach, just get rid of rows with missing data. But you often end up throwing away too much valuable information that way. Then there's constant substitution, like filling in with unknown or maybe a zero. That's pretty basic, though. The more sophisticated strategy is imputation. This is where you substitute that missing value with a plausible estimate. Now, you could use something simple like the mean or the median of the column. That's very common. But more advanced data scientists now often use predictive methods. They actually leverage machine learning algorithms. There's one in Python called iterative imputer, for instance, which cleverly estimates the missing value based on all the other features in that record's data set.
Wow, okay, that's a massive step up from just plugging in the average value. That sounds much smarter. All right, second huge challenge you mentioned was uniqueness, which leads to entity resolution. This sounds tricky. We might have, say, 3 different systems, all talking about the same customer, but maybe they use different IDs or slightly different spellings of the name. How do we figure out they're all the same person and unite those records?
Yeah, this is absolutely critical for the UN and ACUCVT uniqueness. It's
Yeah.
about making sure that John Smith at 123 Main Street from your sales system is correctly identified and linked to, say, J. Smith, with the primary email, jsmith@corpse.com, that might be sitting in your inventory or marketing system. We use techniques like deduplication, obviously, but also more complex record matching. And honestly, the Python library Pandas is often the real workhorse here. It has methods like drop duplicates, which is simple, but more importantly, the really sophisticated merge operation. That lets you intelligently combine records from different tables or files based on finding similarities in key fields.
Which, interestingly, brings us right back to Codd's original problem, doesn't it? Inconsistency. Like if the data says someone's age is 150 years old, that's technically not a missing value. It's not an NULL, but it clearly violates the, logical constraints of the real world.
Exactly. Inconsistency means the data violates its logical meaning. Another classic example might be seeing the city Monza listed as being in the province of Bergamo in Italy, when any Italian knows that's just wrong.
Yeah.
Codd's original answer to prevent this kind of thing was normalization. It's an a priori approach, meaning you design it in from the start. You structurally decompose your tables based on rules called functional dependencies. The whole goal is to eliminate redundancy and therefore prevent these inconsistencies from ever even getting into the database.
Right. Fix it at the source.
Fix it at the source. But let's be honest, in the real world, we rarely get the luxury of designing a perfect database structure from scratch for all our data. So the data scientist very often has to fall back on a posteriori cleaning after the fact. This usually means rule-based cleaning implemented directly in their Python code. They end up using libraries like Pandas to write some very complex queries that flag every single record that violates those known real-world integrity rules. And honestly, that's often the hardest, dirtiest part of that whole 80% preparation time.
Okay, let's zoom out a bit then to the macro level. Data hardly ever sits neatly in one single box, right? We're always having to combine data from different, often autonomous and heterogeneous sources. So how do we approach integrating all this stuff, and why is the choice between ETL and ELT so important strategically?
Yeah, integration is key. The choice between ETL and ELT really boils down to when you want to pay the, let's call it the cleaning tax. ETL stands for extract, transform, load. This is the traditional model, often closely tied to the concept of a data warehouse. You collect the data, extract, then you clean it, harmonize it, make it perfect. That's the transform step. And only then do you load the resulting sparkling clean data into your central repository. It relies on a fairly rigid upfront process. We sometimes call this schema on write. You define the structure before you write the data.
Okay, schema on write for ETL. And ELT, how does that flip it?
ELT flips it. It's extract, load, transform. This is the more modern approach, often favored in the big data world, especially with data lakes. Here, you extract the raw data and you immediately load it as is messy, raw, whatever, into your storage system, like a data lake. You only pay that cleaning tax and actually transform the data much later, usually right when a data scientist needs to query it for a specific analysis. We call this schema on read.
Schema on read. Much more flexible on the way in.
Exactly. It's generally much faster for just getting the data ingested, but it does shift the complexity. The burden of cleaning and making sense of it falls more heavily on the analyst at query time.
That distinction really helps clarify the differences between the three main types of data repositories we hear about. We know the operational database, DB, is great for fast transactions, but pretty bad for looking at historical trends. So let's compare the two big analytical powerhouses, the data warehouse and the data lake.
Right, the data warehouse, PW, is the classic, structured, history-focused repository. It's purpose-built for business intelligence reporting, that kind of thing. Because its main job is analysis, the data, after it's gone through that ETL process we talked about, is typically stored in denormalized formats. Common structures are called star schemas or snowflake schemas.
Hang on, denormalized. We just spent a good chunk of time talking about how COD championed normalization for consistency. Why on earth would you denormalize data in a data warehouse? That seems backward.
It seems backward, but it makes sense when you remember the goal has changed. Normalization is primarily for operational consistency and reducing update anomalies in transactional systems. Denormalization in a DW is all about analytical speed. Think about it. If you store a customer's name and their full address repeatedly right next to every single transaction record they ever made.
Okay, yeah, that's hugely redundant.
It is hugely redundant, which is bad for consistency if you need to update that address. But when an analyst runs a big report looking at sales trends by region, they get all the necessary information that the transaction details, the customer name, the address, all in one massive pre-join block. They don't need to perform those slow join operations across multiple tables. It's optimized purely for retrieval speed during analysis.
Ah, okay. Trade-off. Consistency versus query speed. Makes sense. And the data lake, then, is the really radical alternative to that highly structured data warehouse approach.
Yes, exactly. The data lake, DL, is kind of like managed chaos, or maybe chaos containment is a better term. It's designed to store absolutely everything. Structured data from databases, semi-structured data like JSON or XML, even totally unstructured binary stuff like images or videos, BIL-OBS again. And crucially, it stores it all in its raw, native format. It thrives on that schema on read principle we mentioned with ELT. The philosophy is, you might not know today exactly how you'll want to use this data tomorrow, so just save everything now. You only impose structure and meaning when you actually retrieve it for a specific analysis.
So super flexible, but maybe more work later.
Highly flexible, yes, but often requires significantly more effort from the analyst or data scientist to explore, clean, and prepare the data before it can actually be used effectively.
Now, if you're managing any of these systems, especially at scale, and particularly if they're distributed across multiple machines, you inevitably run headlong into a very famous constraint in computer science, the CAP theorem. What's that about?
Ah, the CAP theorem. Yeah, that's the fundamental trade-off you face in distributed systems. It was proven by Eric Brewer. It basically dictates that any distributed data store can only guarantee 2 out of 3 highly desirable properties. Those properties are Consistency, availability, and partition tolerance.
Okay. Consistency, availability, partition tolerance. Pick two.
Pick any two. You can't have all three perfectly all the time. So consistency means every read receives the most recent write or an error. Basically, everyone sees the same data at the same time, like you'd expect from a traditional relational database. Availability means every request receives a non-error response without guarantee that it contains the most recent write. The system is always up and running. And partition tolerance means the system continues to operate despite network partitions, meaning even if messages get dropped or delayed between different nodes in the distributed system.
So you have to sacrifice one. What's the usual trade-off?
Well, partition tolerance is something you usually can't sacrifice in most modern distributed systems because network failures happen. So the real choice is often between consistency and availability. Traditional relational databases, for things like banking, typically sacrifice availability under partition to guarantee consistency. The CA model, though CP is more common in practice for distributed SQL. Many large-scale web systems, like some NoSQL databases designed for high traffic, often choose to sacrifice some degree of consistency to ensure high availability and partition tolerance, the AP model. They might tolerate temporary inconsistencies that get resolved eventually.
Fascinating. Okay, let's pivot back down to the ground level then. For the individual data scientist who's grappling with all this underlying architecture, how do they actually bridge that gap between the complex database infrastructure and their day-to-day analysis work, which is often in Python?
Right, the crucial bridge there, 9 times out of 10, is the Pandas data frame. It's central to the Python data science ecosystem.
Mm.
And understanding the philosophical difference between how you interact with it versus SQL is really key. SQL is fundamentally declarative. You tell the database what data you want, select these columns from this table where this condition is met. You don't specify how the database should retrieve it. The database management system, DBMS, has its own optimizer to figure out the most efficient way, often working with massive amounts of data stored on disk.
Right, you declare the result you want. And pandas.
Pandas is largely imperative. You typically specify the exact step-by-step procedure you want to perform. Load this data into memory, now filter it using this specific condition, now perform this merge operation, now calculate this new column. And crucially, Pandas primarily operates in memory. This makes it incredibly flexible and fast for interactive tasks like cleaning data, doing imputations, exploratory data analysis, visualizations basically, all that 80% groundwork we keep talking about.
Okay, but the good news is, for people who maybe learn SQL first, the core concepts translate pretty well over to pandas, don't they? Your standard SQL select and from for picking columns. That maps pretty directly to selecting columns in a pandas data frame. Your SQL where clause for filtering rows. That translates almost directly to using conditional filtering in pandas, using Python's logical operators like N for AD and for OR, and that absolutely foundational SQL join operation for combining tables that's mirrored very closely by the powerful pd.merge function in pandas.
Exactly. The mapping is quite intuitive once you see it. And the real magic, the piece that connects the Python world directly to those external databases, often comes down to one specific function, pandas.io.sql.readSQL query. This function is brilliant. It lets your Python code send a complex SQL query directly to a remote database. Could be PostgreSQL, could be MySQL, whatever. Have the database do the heavy lifting of executing that query efficiently on potentially huge tables. And then it pulls the resulting clean data, the result set of that query, directly into a Pandas data frame right there in your Python environment, ready for immediate analysis or further manipulation. It keeps the data retrieval work inside the optimized database server where it belongs.
That's incredibly useful, and given the sheer number of different database types out there, relational, NoSQL, cloud databases, we probably need some kind of unifying tool to talk to all of them without writing custom code for each one, right?
Yes, absolutely. Managing connections and syntax differences across dozens of DBMS types would be a nightmare. That's where tools like SchoolAlchemy become incredibly valuable. SchoolAlchemy is what's known as an object relational mapper, or ORM, but it also functions as a powerful database abstraction layer. Essentially, it abstracts away many of the underlying differences between various databases. Whether your data happens to live in SQLite on your laptop, or a massive Postgres cluster, or a MySQL server, SchoolAlchemy can provide the data scientist with a single, unified Pythonic interface to query and interact with it. It dramatically smooths out that whole data integration pipeline.
Okay, so wrapping this all up, what does this entire deep dive mean for you, the listener? Well, you might not be asked to design the company's main data warehouse tomorrow, but really internalizing the difference between, say, relational consistency and NoSQL flexibility, or understanding why you might deliberately use denormalized storage for analytics, even though it feels wrong, Initially, that's the kind of understanding that separates okay code from really efficient, scalable data science work. And remember that 80% rule for cleaning, it's not going away anytime soon. So mastering those Pandas techniques for handling missing data, for entity resolution, for applying consistency rules, that's absolutely paramount.
And we can't finish without touching briefly on, well, the necessary evil, perhaps, of data management, security and privacy. This is non-negotiable now. Standards like the European GDPR are really important here. They adopt what's called a prescriptive approach, which basically means you must proactively plan for data protection right from the start. You can't treat it as an afterthought. Practically speaking, this means focusing on techniques like the anonymization of personal data whenever possible. If you don't strictly need identifiable information for your analysis, get rid of it or obscure it. It also demands really stringent access control. We're not just talking about general user logins. We mean detailed control, maybe using specific privileges in MySQL, or even defining database views that deliberately restrict access only to certain non-sensitive rows or columns for specific users or applications. And finally, especially given that some NoSQL systems, particularly in their early days, maybe prioritize performance over built-in security features, robust encryption of data is critical. That means encrypting data both when it's moving across networks in transit and when it's sitting stored on disk at rest.
This is vital to ensure privacy is maintained across the entire data architecture. We spent this whole discussion really exploring that fundamental tension, the tension between consistency and speed or consistency and flexibility. Right from COD's strict 1NF aiming for perfect consistency through to modern architectures that often have to make compromises. So let me leave you with a final thought, a scenario to mull over. Imagine you were leading a huge project, maybe detecting financial fraud, processing billions of transactions in near real time. You inevitably hit the limits imposed by the CIP theorem, knowing you have to make a choice, that you can only guarantee 2 out of 3, consistency, availability, partition tolerance. Where would you place your bet? Would you prioritize achieving perfect, normalized consistency across your distributed system, ensuring every transaction is instantly reflected everywhere, even if it meant occasionally sacrificing some availability during network hiccups? Or would you prioritize the sheer availability and ultra-low latency access to that incoming transaction data, getting answers fast, even if it meant accepting a small risk of temporary inconsistencies between different parts of the system? Which trade-off would define your business strategy? That's the kind of hard decision data architecture forces you to make.